Welcome back to Honors Calculus. This video is on evaluating derivatives. We've seen already that the differentiation function is a nice tool for talking about tangent lines and other things related to rate of change of a function. And we've seen that we can use a limiting process to find the value of the derivative at a particular point. We've also found that we can use that limiting process in general on an arbitrary value x in order to find an expression, an algebraic expression for the derivative function in certain circumstances. Here, we're going to build on that idea and find some patterns in how the derivative works and how differentiation works in order to be able to more easily evaluate derivatives of functions without having to go through all of that limiting process. So let me get my head out of the way. And quickly, let's go through the idea of differentiation. The derivative function f prime of x is the result of taking the differentiation operator, which we usually write as d over dx, and evaluating that at f of x, which we evaluate using the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And we've seen previously that differentiation is linear, which means that the derivative of some constant a times a function f of x plus some other constant b times the function g of x is equal to a times the derivative f prime of x plus b times the derivative g prime of x. So if we can find something that will work on one specific case, we can extend that outward and things will work pretty out nicely. Some of the simplest functions that we can possibly work with are the power functions. I'm going to start with the simplest of the power functions. X to the 0 is 1. And let's see what happens when we try to take the derivative of 1. Well, we evaluate f of x plus delta x, and we get 1. We evaluate f of x, and we get 1. So we have the limit as delta x goes to 0 of 0 over delta x, which is the limit as x goes to 0 of 0 or just 0. Moving up the chain of powers. X to the first power, or just x, well, f prime of x is going to be the limit as delta x goes to 0 of f of x plus delta x, which is just x plus delta x, minus f of x, which is just x, all over delta x, those x's cancel out in the numerator, leaving me with delta x over delta x. And so I'm really just taking the limit of 1, which is 1. All right, when we get to x squared, that's when things start to get, I guess interesting is the right word. Well, f prime of x is going to be the limit as delta x goes to 0 of x plus delta x squared minus f of x squared, all over delta x. Okay, and when we expand this out, we get some bit of a mess that happens. We'll get x squared plus 2x delta x plus delta x squared. The x squareds will cancel out, and we'll have 2x delta x plus delta x squared all over delta x. The delta x's can cancel out, reducing the fraction. And as delta x goes to 0, we are left with just 2x. All right, we could keep doing this indefinitely if we want to, but I'm kind of getting bored. So let's see if we can figure out a way to deal with a power function in general. F of x equals x to the nth power. F prime of x then will be the limit as delta x goes to 0 of x plus delta x to the nth power minus x to the nth power all over delta x. If you have seen before, Pascal's triangle, or even if you haven't seen it before, Pascal's triangle, each number in the triangle is the sum of the two numbers diagonally above it. And if there are no two numbers diagonally above it, we treat the empty spot as a 0, right? So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 3 is 6, and so on. The reason that Pascal's triangle is useful is that the nth row of Pascal's triangle gives the expansion of a binomial raised to the nth power. So if we have, like we had in the previous problem, the second power, we had x squared plus 2 times x times delta x times delta x squared. 1, 2, and 1 were the coefficients. If you took x plus delta x and cubed it, you would have x cubed plus 3x squared delta x plus 3x delta x squared plus 1 delta x cubed, and so on down the list. One useful property of Pascal's triangle is that this diagonal, which is going to give us the terms that have exactly one factor of delta x, the coefficient is the power. First power 1, second power 2, third power 3, fourth power 4. It will continue onward like that. So if I expand this out, I'm going to have the limit as delta x goes to 0. I know that I'm going to have x to the n power. I'm going to have n times x to the n minus 1 times delta x. And I'm going to have several more terms. Those several more terms are going to have delta x squared, delta x cubed, all the way down to delta x to the n power. The x to the n's will cancel each other out. So we'll have delta x squared, we'll have delta x cubed, so on going on. I don't care what the coefficients of these things are. I'm putting these question marks because I don't care. The important thing is that when I divide off the delta x, that first delta x will cancel out, and we'll lose one of the factors of delta x in all the other terms here. So I have n times x to the n minus 1 power. The delta x's cancel out. I have something, I don't know what it is, times delta x. I have something, I don't know what it is, times delta x squared. And I keep going however far I have to go. But since we're taking the limit as delta x goes to 0, all of these things go to 0, and I'm left with n times x to the n minus 1 power. I am really big in my courses telling you not to memorize things. Instead, have down at ready reference things that you're going to need to know that you're worried about keeping straight in your head. And then don't worry about memorizing anything. This is the exception to that rule. If you feel that you are a person who is going to pass a calculus class, you should have the power rule for differentiation memorized. It is going to be used so often that it's probably not going to be that difficult for you to memorize it, but I strongly encourage you to take the time and make sure you know this rule on sight. So if I want to take the derivative of x cubed, well, according to my rules here, this is a power rule with n equals 3. So I put down n, which is 3. I put down x, and I raise it to the power of n minus 1. 3 minus 1 is 2. If I want to take the derivative of x to the 7th power, n is 7 times x raised to the n minus 1. 7 minus 1 is 6. That's all that takes. We can extend this rule. The proof that I gave only works when n is a positive whole number. We will see a little bit later on that this will work, but it turns out that this power rule will work even if that's not the case. If I want to take the derivative of the square root of x, well, the square root of x is the same thing as x to the 1/2 power. And so I can use the power rule with n equal to 1/2. I will get 1/2 times x to the 1/2 minus 1, which is negative 1/2 power. And then playing around with properties of exponents, I can write that as 1 over 2 times the square root of x. I can try to take the derivative of a fraction, something like the derivative of 1 over x cubed. Well, 1 over x cubed is the same thing as x to the negative 3 power. So now using n equals negative 3, I'll write down the derivative, negative 3 times x, negative 3 minus 1 is the negative 4th power. And then cleaning up with properties of exponents, that's negative 3 over x to the 4th. All right, there's the power rule in action. Now that we have the power rule, we can extend our idea and also take the derivative of a polynomial. If I want to take the derivative of 3x squared plus 5x plus 7, I can use that property I mentioned at the beginning of class that we showed in a previous video. Linearity. The derivative of 3x squared plus 5x plus 7 is 3 times the derivative of x squared plus 5 times the derivative of x plus 7 times the derivative of 1. The derivative of x squared is 2x. The derivative of x is 1, and the derivative of 1 is 0. So all told, the derivative of 3x squared plus 5x plus 7 is 6x plus 5. That is so much easier than the task we were looking at previously, trying to plug this into the limiting formula, work through all of that, tear our hair out with the algebra. When we have functions that we can work with like this, it really is this straightforward. We just go through and we use the rules that we know. As you get comfortable with this, after this video from now on, whenever I'm taking the derivative of a polynomial, I'm going to write down the solution without going through the intermediate steps. If you feel comfortable and confident in doing that yourself, go for it. There's nothing wrong with that. If you're a little bit shaky and you're not quite sure where everything is coming from, writing out the intermediate steps is never a bad thing. There is never any penalty for writing too much. There can be a lot of confusion for writing too little. All right, let's take a look at one more problem just like that before I go on and look at a couple of other applications. A nice large polynomial, fifth degree polynomial. 27x to the fifth minus 19x to the fourth plus 21x cubed minus 11x squared plus 43x minus 196. But it's a polynomial, so I can use linearity and I can use the power rule to evaluate this relatively effortlessly. I'll have 27 times the derivative of x to the fifth, which is 5 times x to the fourth. I'll have 19 times the derivative of x to the fourth, which is 4 times x to the 4 minus 1, which is 3. Then I'll have 21 times the derivative of x cubed, which will be 3x squared, minus 11 times the derivative of x squared, which is 2x, plus 43 times the derivative of x, which is 1, minus 196 times the derivative of 1, which is 0. Right? Derivative of any constant is a 0. We can get rid of that term without even having to think about it once you get into this habit. All right, 27 times 5 is 135. 19 times 4 is 76. 21 times 3 is 63. 11 times 2 is 22. 43 times 1 is 43, and there we have it. We've taken the derivative of this terrible polynomial. Now that we have a tool that lets us take derivatives relatively quickly, we can expand our search and talk about higher order derivatives. For our function, we defined the derivative f prime of x as the differentiation operator acting on f of x. If I want to take the derivative of this thing, I will have f prime, and then I'll prime it. So I'll get f double prime. The meaning is the derivative of f prime, and that's how we'll calculate it. But I do want to mention that when you're chaining these derivative operators together, a notation that you'll frequently come across is that it's d squared over dx squared. The operator acting on the operator, we write using this squaring notation. And we can keep going. The third derivative is written using f triple prime of x. And at this point, all of these primes are getting a little bit messy. So instead of continuing on with that chain, higher order derivatives than that, we tend to put the number of primes that would be there in parentheses. So f with a superscript 4 in parentheses is the fourth derivative of f at x. And it is in fact the derivative of the third derivative and if we wanted to, we could keep going, but applications of the first derivative are all over the place. Applications of the second derivative exist, but are a little bit less likely to occur, although the second derivative has one very important application in kinematics that I'm going to talk about in just a moment. I've seen applications of the third derivative. There's one really interesting application of the fourth derivative that I know that has to do with structural engineering and the resiliency of a cantilevered steel beam. It is literally the only place I've ever seen a fourth derivative, and I have never in my life seen an application of a derivative higher than that. But they still exist, they still work, and we can still do things with them, and sometimes that's what really matters. And in fact, we can name them. You have probably heard at some point in the past that Sir Isaac Newton, the famous physicist, invented calculus. He invented calculus for a completely different reason than what we're talking about here, but he invented it to solve a physics problem. Another mathematician, Leibniz, was also developing some of the ideas of calculus at the same time, and Leibniz was really working in the study of kinematics. And in kinematics, we switched from having f as a function of x to writing x as a function of t. and we call that the position of a particle. So at time t, the particle is in position x. Velocity is the change in position over time. And the derivative is telling you how something is changing over time, right? The slope of the tangent line. How fast is this function changing? If we think about how fast the velocity is changing over time, that's a thing called acceleration. Here again, we come to Newton. Newton's second law, F equals ma. Force is mass times acceleration, which is the second derivative of position. So if we can learn how to handle derivatives, and we can learn how to take derivatives and how to undo derivatives, if we know stuff about acceleration, we can talk about stuff that has to do with position. That's the branch of mathematics called differential equations. Differential equations is the heart of kinematics and the heart of most of the physical sciences. And it always comes down to differential equations involving second order derivatives, because acceleration is the second derivative of position, and acceleration shows up in Newton's second law. So acceleration is useful. It is in a lot of ways the big idea, but we can keep going. A change in acceleration over time is not something that often gets studied in general physics courses, but it is a thing that exists. It's called the jerk. If you think about a car where you have very touchy brakes, and you're trying to slow down gently, but your brakes are very sensitive, so you hit them a little bit too fast and you slow down way too fast and you feel like you're being jerked around. The change in acceleration is happening too fast. A change in jerk that is happening too fast can cause injury. The phenomena of whiplash, when you come to a stop so quickly that you snap your neck, or the snap that a whip makes when you throw it forward and then pull it back incredibly quickly. Snap is the fourth derivative of position. And again, I've never seen an application of higher order derivatives than this, but they exist and they have been named, and I'm sure that someone is studying them. If you take the derivative of a snap, you get the crackle. And yes, if you take the derivative of the crackle, you will get the pop of the position. I am not making that up. That is the names that these things have been given. They are not studied very often, but physicists cannot be said to not have a sense of humor. All right. So if we are looking at a function and we want to find a higher derivative, I did mention that the way to do that is to find the successive derivatives. So we start with our function f of x, and the first thing we will need to do in order to find the second derivative is to find the first derivative. The derivative of x squared is 2x. The derivative of x is 1, so the derivative of 3x is 3. The derivative of a constant, 5, is 0. Then from here, we can continue onward. The second derivative is the derivative of the first derivative. The derivative of x is 1, so the derivative of 2x is 2. The derivative of any constant is 0, so the derivative of 3 is 0, and that's all we're left with. For the function x squared plus 3x plus 5, the second derivative, f double prime of x, is equal to 2. All right, and that's where I would like to give you one to try on your own. For the function f of x equals x cubed minus 9x squared plus 6x plus 7, I would like you to find the second derivative, f double prime of x. All right, that's all I have for you. Take a few minutes, see what you can do with this one. Hopefully you find this process of using the power rule to take derivatives fairly straightforward. See what you can do on this problem, and I'll see you in the next video.